Okay, so we're going to look at a particular type of distribution in statistics and probability, and it's called a normal distribution. Okay, and I suppose in order to kind of build up to that normal distribution idea, I suppose it's important to look at just what we even mean by that in general. So that idea of distribution of data, I suppose, generally in terms of statistics here. And this is kind of what we have in the first instance here. So we are looking, first of all, I suppose, at data that's skewed to the right, and that's where we have a tail, as you can kind of see here, of some data which is up to the right hand side, which is kind of, and most of the data I suppose is kind of collected around the left hand side here, as we can kind of see. Okay, most of the information is definitely to the left there, but there is some information to the right. So we consider that to be skewed right because there's a kind of tail kind of pulling it to the right hand side a little bit. Okay, whereas opposed otherwise all of the information would be quite central, but it's only really right that the data is kind of leading, I suppose, is what I'm trying to say there. And that's going to have an impact on our three different types of, I suppose, our three measures of central tendency or average there. So the mode obviously is the most often one. So the mode will stay where most of the data is. Okay, the median will be slightly skewed to the right hand side because it's that middle value, so it's still fairly central. And then that should be the mean, of course, there as the last one. The mean here is going to be the most affected by those values up to the top. And I suppose these, in this sense, could be considered your outliers, as it were. Okay, those values that kind of don't fit in with the rest of the information in the data set. Okay, looking, I suppose, then at some of the next parts, so skewed to the left, very, very similar, I suppose, just the opposite case. Most of the information to the right, some of the data pulled to the left. The mode stays where it is with most of the information. The median, again, is quite central, and then the mean is skewed to that left-hand side, being pulled or affected by those outliers again, as with the skewed to the right distribution. Jumbled all around, okay, the technical term, as it were, but all the data being kind of all jumbled around. There's no clear distribution there. There's not a clear kind of center for a lot of the information. There is a modal range there for a kind of histogram shape in the 5 to 10 interval there. We can see that does seem to be the most frequent interval, but otherwise there's no clear pattern to the distribution is kind of what we're getting at here. Now, in a lot of distributions or different examples we're looking at, the data will be somewhat symmetrical. Okay, it mightn't be entirely, but it will be quite symmetrical. And we can kind of see the example here where we have a histogram with a lot of the data in the center, okay, in the kind of central region or interval of the data there, and then on either side there is a fall or a drop off, but it's roughly a similar fall on either side. Okay, we can obviously see there is some discrepancy here in the example that we have, and I suppose that's why we're saying this is roughly normal, because a normal distribution will follow the bell-shaped curve that's kind of marked in here. So this idea that it will increase to a peak in the center and then fall in the same way on the other side, so completely symmetrical, and essentially that if you were nearly in that 5 to 10 or 15 to 20 interval, that you would nearly come out with very, very similar, if not identical, frequencies on either side there, were this a normal distribution. Okay, and this normal distribution is one of the key distributions that we use in statistics, and it's one of the biggest, I suppose, ones that you're going to be looking at across your study of statistics as part of Leaving Cert here. So I suppose that's the one that we're going to spend the most time on. It is important to be able to describe data generally, as we've done here, skewed to the right, skewed to the left, and have some understanding of how that will affect our measures of central tendency, as we've talked about here. But really a lot of that is just relying on your understanding of what those measures of central tendency are in general. So as I said, like the mode is the most common, that's going to stay where it is, where most of the data is. The median by definition is the middle value of the data set when it's ordered, so it tends to still stay fairly central, no matter kind of how the data is skewed. The mean, I suppose, is the most affected nearly by those outliers, because they do, and we would have said that obviously when we looked at the mean in the first place. So getting more specifically into the normal distribution here. So it's a very, very important distribution in statistics in general. It's symmetrical, which is, I suppose, a key trait of the distribution and a very important and useful trait for us. It has mean mu in the center. Okay, so even in this case, 0 in some cases, but we'll start with mu here for first of all. So mean mu in the center, and then a similar amount of data to either side of that kind of middle average value. So we can see there mean, median, and mode, all three in the center of the distribution. Because it is symmetrical, the mode, the most value or the most information, the most often there is in the center. The median, again, the middle value, going to be quite central, and then because of the symmetry there, the mean also falls with that same value. So ideally, this is kind of in a perfect distribution, those three nearly do end up being the same value. Our distribution, as we said, symmetrical and following that bell-shaped curve. 50% of the information is above the mean, 50% below the mean, again just tying back to the symmetry there, and the area under the curve is equal to the total probability of you getting any particular value in that curve, which is 1. Okay, so that's something we're going to get into in a little more detail, but in general, the area under the curve there is considered to be 1, or 100% of the information is contained underneath the curve there. You'll notice even as well that we do have different markings here above and below, using our notation here of sigma, which stands for standard deviation. So the standard deviation, as we would have said when we looked at it or introduced it first, standard deviation is the average distance from the mean. So by looking at all of the kind of data points and calculating their individual averages from this mean value, we can work out the, I suppose, average distance from the mean here. And working with, I suppose, that amount of information can kind of allow me to consider what is maybe a value that is far from the mean, what is a value that's actually quite close to the mean, how extreme is a particular value that I have in my data set or that I've encountered in an experiment here. And it just allows me maybe to comment on that a little bit. It's important even just to know in setting up a normal distribution that idea of having one standard deviation either side, then two standard deviations either side, and being able to fill in those values if you are given them. Like if I'm told the mean is 50 with a standard deviation of 5, that I would be able to then apply that and know that the 50 in the center, 55 here, 60, 45, 40, and so on and so forth. Okay, so just being able to fill out a normal distribution. I suppose going even more specific than just a normal distribution, we have what we call the standard normal distribution. Okay, and standard, I suppose, here is in quite a specific or traditional sense of the word standard, and that idea of something being standardized. Okay, so I suppose the idea here, standardized, or I suppose we could even make a note of kind of that idea of comparison. So by standardizing things or using a standard kind of metric, we're better able to compare information. And that is one of the big uses of this normal distribution and the standard normal distribution more specifically. So it's sometimes called our Z distribution. Okay, and it's a special case with mean 0 and standard deviation 1. Okay, so this allows us to comment specifically on a lot of the information in a set, in a distribution, okay, in a normal distribution here. A Z value represents the number of standard deviations from the mean. Okay, this is kind of a key point for working with the normal distribution and the standard normal distribution. If we can calculate a Z value, we can use that to talk about the number of standard deviations from the mean. And as we've kind of said, looking at standard deviation, it's the distance, that average distance from the mean. So if I work out a large standard deviation, that will suggest that my value is quite out of the ordinary, or is quite an extreme value with comparison to maybe a more typical value, which is, I suppose, what the mean is there. And that can be very, very useful for us in comparing data, and it can also be useful for us in working with probabilities and those sort of things that we'll see later on. So continuing onwards, we'll look at, I suppose, the applications of this distribution, which falls in the realm of Z-scores. Okay, so Z-scores, coming back to that idea of standardizing and allowing for comparison, we've seen that the standard normal distribution is quite a good one for comparison because we have that idea of it relating to number of standard deviations from the mean. Okay, and allowing maybe us to better compare different information irrelevant of whether the mean is different in the distributions there, or whether the standard deviation necessarily of the individual kind of values are different. It just gives us more comparison and better, more standard comparison across different data sets. So ideally we would like to be able to convert perhaps normally distributed data into standard normally distributed data, and we do have a formula for that, our standardizing formula. Okay, and this is given to you in your formula and tables book. I would say the key thing is just to know when you're being asked to use it. So you're really being asked to use this any mention of normal distribution, of mean, of standard deviation, and of a particular data point. Okay, and we'll see maybe later why I'm stressing that. But this would be where I'm being asked to maybe look at specific values or a specific data point or value that was achieved in a test or a score that was received in a race or a height value, a specific value, and comparing that with our kind of average value for a particular population. As we said, z-scores represent the position of the data with respect to the mean, using standard deviation as the unit of measure. So really all that means is how many standard deviations is this value from the mean, and in what direction as well. Okay, so the signs are important here because they do give value, they do give greater meaning to the information that we're looking at. So whether I have a positive z-score, that's going to mean that my value could be above average, okay, because it's a positive number of standard deviations away from the mean. And then similarly, if I have a negative value, then I could consider maybe that my value is below average or is below the mean because of that negative result that I've received with it there. So we look maybe at how that can be applied in an actual situation and why standardizing is considered to be useful for us. So the percentage results in a maths exam for a class had a mean mark of 70 with a standard deviation of 15. The percentage results in an English exam for the same class had a mean mark of 72 with a standard deviation of 10. The results in both exams were normally distributed. Mary got 65 in maths and 68 in English. In which exam did Mary do better relative to the other students in the class? Justify your answer. Okay, so a good example here of why z-scores, I suppose, are considered to be useful or how they can be useful in comparison. We're looking at data sets here which do not have the same mean or do not have the same standard deviation individually, but we want to be able to compare the two. Okay, it's not enough to say that Mary has done better in English, for example, for getting 68 in English, because even just by looking at the mean there, the mean was higher in English than it were in maths. In maths, the mean was slightly lower, so although she has gotten a lower mark overall, that could actually end up being a better result by comparison to perhaps the rest of the class, okay, or the rest of the data. So I suppose that can be where a lot of this comes into play, is maybe comparing one data point with reference to the other data points or the rest of the data set, and allowing then comparison with a different data set as well, but under the same kind of setting or under the same kind of measurements, I suppose, or kind of units of measure. So we look at converting these z-scores here. We'll start with her math score, which was 65. Okay, we're going to have to use our standardizing formula here. So z equals x minus mu over sigma. I'll fill out all of these values. The x value, I suppose, is going to depend on which of the two questions I'm doing. Mu is the mean value, which is 72. Sigma is the standard deviation, which is 10. Let's start with her value from maths, which is 65. So it's 65 minus 72 over 10. So let's see what that gives us here. So 65 minus 72 over, 65 minus 72 over 10. And that is minus 0.7. Let's look at her other value in English, 68 minus 70. Or excuse me, that should be 70 there for maths. Sorry, I'm looking at the two differently. So that'd be minus 5 over 10. Sorry, yeah, that's better idea. Excuse me, 0.5. And then looking at the 72, of course, goes with English there. The percentage results in English had a mean of 72. And the standard deviation, oh, excuse me, we're making a mess of this one. So standard deviation, excuse me, here is 15 as well. Right, let's see. Third time's the charm. Minus 70 over 15. This is what I get for not highlighting. Minus 0.33. Okay, or minus a third. So minus a third here. Okay, let's highlight for the next one. English exam. Mean of 72. Standard deviation of 10. Let's fill them in. So 72, 10. And that's going to give me 68 minus 72 over 10 minus 0.4. Okay, so comparing the two results, in one result, her result here is a third or minus a third of a standard deviation, or minus 0.33 standard deviations below the mean. Her English result is minus 0.4 standard deviations below the mean. Okay, so her specific result in maths, she is minus 0.33 standard deviations below the mean. Okay, and in English, she's minus 0.4 standard deviations below the mean. Okay, so comparing the two obviously is better to be less standard deviations below from the mean or away from the mean. So Mary has done slightly better in maths than she did in English. Okay, so Mary did better in maths, only minus 0.33 standard deviations below the mean. So she's much closer, not much closer, she's a slight, tiny little bit closer to the mean in maths than she is in English. She is below the mean value in both assessments there, okay, relative to the class. She is kind of falling below the mean value there, but slightly less below in maths. And I suppose less than 5, I shouldn't say less than 5, less than half a standard deviation in both cases. So she is quite close to the mean all the same, particularly with reference to kind of standard deviations there. When you consider, like, on the right hand side, a standard deviation is 10. So minus 0.4 of that is small enough, I suppose, 2/5 of a standard deviation away from the mean. So she's still quite close to that mean value in both cases, but I suppose slightly closer in maths than she is in English. Okay, and I suppose that's just one example of how this can be used in comparison and why it might be useful. So allowing us to compare specifically the values there without with kind of just reference to a general unit of measure as opposed to the specific results in each exam there. And it just makes for easier comparison because the units are the same. So I suppose that really is why we would lean towards that. The only things in the question that pointed me towards that were reference to mean, standard deviation, and I suppose comparison of 2 marks there are the things that would kind of lead me towards that. So what we'll do is we're going to look next at the probabilities and how I can use these z-scores in calculating the probability of achieving a certain value that is maybe a given number of standard deviations away, or achieving or what value I would have to achieve to maybe result in a certain probability, and kind of working between the two of those there using our standardizing formula and using our z-score values.